Thank you. This is the last session of the Earth's interior neighborhood, Centennial Central. So thank you for staying around for this last hour. During this hour, we're going to focus on energy and energy resources as sort of our final component of Earth's habitability. So we have a variety of different speakers today who are going to talk about different aspects of energy, energy alternatives. And our first speaker is Cinti Lee, and he is going to tell us a little bit more about critical minerals and how that relates to the larger picture. So Cinti?
That's all I need, I think, right? Okay, thank you to the conveners for inviting me. I'm going to talk about the role of Earth scientists in this energy transition. Well, basically our goal, our hope is that with time, we can transition off of fossil fuels towards a renewable energy portfolio. And so what I want to talk about is the challenges that lie ahead to, one, make this faster, and two, what is the role of Earth scientists in playing in helping this through. So this figure is, the y-axis is coming from the UN Human Development Office. The y-axis is basically the HDI index, the happiness index or quality of life index, and the x-axis is the per capita energy usage. And there's this correlation that we have with the United States being the biggest country that's way up over there at the right. Our per capita energy usage is the highest. And so as we look forward to project to the future, all these countries, they're going to want to start to live like Americans, consume as much as us. The size of these circles are related to the size of the population. So at the same time, we're also going to see population growth in some of these countries like India and China and all the ones in Africa. And so if you try to project the energy use going forward, you'll find that, did I skip one here? Oh no, okay. This is, oh, anyway. The projected energy use is a combination of growth in population and our basic per capita energy usage. And Asia is going to be, at least the next 50 years, the largest growth. After that will be Africa, okay? And so the way to look at how we use energy is this simple diagram I have called about sustainability. And you have to think about population as well as the amount of energy we consume, or the happiness index. And all of that can be supported by, as long as we have ready access to food, water, health, material wealth, we can continue to grow our society and have a peaceful world. And of course, if you have, all of those require energy, and so you have unlimited access to energy, you can keep on growing things indefinitely, in theory. Of course, with consumption of energy, there are all these negative impacts. We know the negative impacts of hydrocarbons or fossil fuels, that's climate change, but there are also impacts of the renewables. We have to pull in mineral resources to that, and that affects land, water, and potentially air and biodiversity. In any case, anytime we use energy, there's no free energy. The negative impacts on the environment go back to affecting access to food, water, et cetera. That helps reduce the growth rates of the population. And at the same time, population growth has direct impacts on the environment. So all these negative feedbacks will actually limit us from growing to the type of peaceful global community that we actually want. And I just show these pictures right here. This is from Madagascar, where I was just at recently. There's not many forests left there. It's a biodiversity hotspot, but there is one of the largest cobalt mines out there that's supporting our ability to make lithium cobalt batteries. So nothing is really clean. And so the key is really to look at all the factors here so that we can make a strategic plan for the future. So we want to make this transition to renewables, but we're not going as fast as we can. And there are many reasons why we can't go that fast. And I'm only going to talk about some of them. But the most important ones right now are with the renewables, energy storage. We still haven't come up with a game changer plan for energy storage. Right now, it's lithium cobalt batteries. And we also had the problem of efficient transport of electricity or the energy from point of source to points of use. And if we want to change all of that, we are going to stress our supplies of lithium and cobalt for the batteries and copper to revamp our entire electrical grid. So here, if you project, look at current energy use, this is from BP. Right now, the amount in our portfolio of renewable energies, at least solar and wind, is very small and it's growing fast. But in order for it to really make a difference so that we become carbon neutral, you can see how much we have to change in terms of converting our fossil fuel energy to renewable energies. It's a huge undertaking that we have to go if we want to bring up populations and also our ability to quality of life. So we've put up this simple framework for sort of estimating how much reserves that you have. This is to place all of this into context if we want to make this any transition right now. What are the challenges that we have? So this is an equation showing the lifespan of the reserves, and reserves are how much minerals are in the ground that can be extracted economically in a reasonable amount of time, and that extraction rate with the long term matches your demand. And of course, with demand, you'll continue steadily to decrease your reserves until there's nothing, unless you recycle or unless you have higher efficiency ways of processing the metals, and or you can convert resources to reserves by exploration or technological advancement. So this equation, I don't want to get into details, but basically you can pick out every single term in there, and if you want to move forward, how do we control these terms in the next 10 years? Okay. So I can take that with current estimates of reserves. This is based on some USGS data and our own compilations, and this is the projection of how much time we have left for if we were to assume that everyone wanted to live like an American in this world. And no population growth and no transition to renewables, just living like what we are now. And so the US, you can see, it looks very grim. Lithium doesn't last more than 10 years. This is our own reserves. So we're going to have to depend on other countries to get our lithium if we want to go all renewables. You can look at the global supply, and if the entire world cooperated and shared all their resources in a really idealistic world, we might have, it doesn't actually look that bad, 100 years of lithium, and with exploration, we'll be fine. Rare earths, we're going to be fine. This, of course, doesn't account for other issues like geopolitics. Now, we can look at this again, where let's try to convert all of our energies to renewables, get rid of fossil fuels completely, and what you end up with is something that looks even grimmer, that there is no way for the US to survive on its own, and the global population will not be able to survive very long with this sort of energy supply. So what I'm going to do is move to some of the elements, just talk more about geology for a second, because I want to get a lot of people here doing basic research, and I want to show how exciting studying minerals or deposits actually are. So this is lithium. There's about 62 kilograms of lithium carbonate equivalent in your typical electric car battery, and most of it is found in Australia and Chile. And these are just pictures of the deposits in Chile. Basically, they're formed in brines, basinal brines, high up in the Andes, and you pump that stuff out, and then through a series of evaporative steps, you start to concentrate it and purify, and then that semi-raw material you actually send back to China to get processed to become finally lithium cobalt batteries. And why do they occur primarily in the Andes, or at least these types of lithium deposits? And we got very interested in that because the general view is that lithium comes off the subducting slab. It's a fluid mobile element, but we're showing that that's probably not the dominant way of enriching lithium. Instead, what happens is lithium is just enriched because you have extreme amounts of magmatic differentiation. So these are continental arcs, and the thicker the crust, the more these magmas differentiate, and the residual liquids or magmas become more and more enriched in lithium. So you get these andesites and these rhyolites that have high lithium contents, and they're the source rocks. And with weathering and transport of dissolved lithium in solution in the groundwaters to these basins, which happen to be at high elevations because you have this thick crust, and they also happen because they're in these high elevations, they're endorheic, net evaporative. then you get this additional secondary concentration that goes on. So this is why the Andes have lithium and very few other places in the world have lithium. So geology is very specific on where it gives you lithium. And for those doing more basic research, I mean, this is applied research, understanding how you form a lithium deposit. This connection with the crustal thickness is actually something very profound. You can look at silica versus the composition of the arc lavas as a function of elevation, which you would think, why would anyone ever do that? But elevation correlates to crustal thickness. And if you, those of you who are interested in how continents form, just this fundamental question, how do continents form on the Earth? Well, this is probably 90% of the problem. It's not just the composition, but it's about thickening of making the crust. I'll go to copper. Copper is another interesting one that we need for our electrical grid to revamp our aging infrastructure. And copper is primarily found in these porphyry deposits in arc systems. And not just any arc system, they tend to be in continental arcs, thick crust, kind of like in lithium. And they have these funny geochemical signatures that relate to this guy, strontium yttrium. The porphyries with copper have high strontium yttriums, and the ones without copper don't have high strontium yttrium. All you need to know is that high strontium yttrium, one possible explanation for that is that this mineral, garnet, plays a big role in the genesis of the host, the magmas that bring up the copper. And the garnet is an element, a mineral that's preferred under high pressure differentiation. So it makes sense it's coming in thick continental crust arcs. And the garnet, what it does is when it fractionates, it doesn't actually take a lot of ferric iron. It takes ferrous iron. And so the residual magma becomes enriched in ferric iron and becomes more and more oxidized. And when it becomes more and more oxidized, is destabilized sulfide, which would otherwise pull out copper and never let you get copper to the surface. But it mobilizes that copper into late-stage fluids, and that copper that can migrate to the tops of the magma bodies and form these copper-rich cupolas that we can actually tap for the ores. And so understanding the transport of these metals like copper is you've got to bring in this fundamental petrology, but you also need to understand tectonics, maybe climate, maybe geomorphology. It's a really interdisciplinary field that I hope there's so many bright minds here at AGU. Maybe it's time to come to work on these sorts of things together as a team. The last element I want to talk about, which is not so important necessarily for renewables, but it's going to prove or set up a point that I want to make, and this is tungsten. And tungsten is very important for hardened steel alloys, tungsten carbide. And in World War II, it was used to make armor-piercing bullets, and very essential for everyone to, I guess, try to kill each other at the time. But we got interested in it because these tungsten deposits form by the reaction of tungsten-bearing magmatic fluids when they are expelled out of the magmas and interact with the country rock, which are sediments, in particular carbonates. They form this mineral called scheelite, the tungsten ore. And there are periods in Earth's history where it seems like everything is aligned to form the type of ore deposit you have. So in the Cretaceous, you have a flare of continental arcs, and these continental arcs intrude all these carbonates, and they make all these tungsten deposits. And we were really interested in this because we're interested in long-term carbon cycling, but a side product was an understanding of tungsten. And so the right-hand figure is a map of all these tungsten deposits where basically you have all this metamorphic decarbonation pumping CO2 out, but at the same time, they're forming ore deposits. Now, this was a global thing, and not all times in Earth's history actually make this. It turns out the largest tungsten deposit is in China, and for this very reason. And in World War II, coming up to it, Japan and Germany, geology wasn't fair to them in that sense. There is no tungsten in those countries, so they needed the tungsten. The Japanese took over the southern China and to get for the source of tungsten, they were using that and shipping that tungsten over to Germany. And then the Americans came in, wiped out that supply chain, and which contributed to helping weaken the Nazis. And there's a lot more to that story that I won't get into, but what I'm trying to say is because geology is not fair, conflict can happen. In this case, conflict is exacerbated by natural resources. But we can go and look at something, instead of building weapons, which is not necessary for us, but energy is necessary. Let's take a look at lithium. This is a very nice paper by Sun et al. About material flow of lithium. The right-hand part is a whole bunch of countries, and this is where lithium comes from, primarily Chile and Australia. And the far right over there is the users, producers, and then it goes to the users as the form of lithium cobalt batteries. And you can see that although most of the ore is coming from Australia and Chile, everything eventually goes to China in terms of the processing. So if you want to go all renewables and you want this energy storage, there's a geopolitical challenge here. You're going to have to rely, in this case, on one country, essentially, that controls all your supply of lithium. The other point I want to make is that anytime you see one of these arrows go from one country to another, there's a very large transport cost associated with that. And with that transport cost comes consumption of energy and a carbon footprint if you're using fossil fuels to transport all of your materials. And so, you take Australia, they crush the rock, but they pretty much send this only slightly modified rock, ship it to China, and in fact, Australia loses most of its value in its ore, and most of the value actually goes to China. But you're shipping this heavy rock all the way across, and then Chile is sending it across the Pacific Ocean. Today, the U.S. has the second largest rare earth element mine in the world, but we still send much of that rare earth elements back to China to get processed. So these are clear examples of where we need to improve on if we want to reduce carbon footprints and enhance efficiencies. So what we've done is to estimate what your carbon footprint might be of a lithium cobalt battery in your Tesla. And this is a conservative estimate. It's based on how much energy is needed for crushing, transport, and then chemical refining and processing. It turns out, of all of these, the biggest energy consumption is just this transport process that we're doing. So your gasoline car takes 4,000 kilograms produces 4,000 kilograms of CO2 per year. Your equivalent electric vehicle, if you allow for a 10-year lifespan for the battery and the entire carbon footprints of making this battery, actually not making it, just processing these elements, is 2,000 kilograms of CO2 per year, which means that if you don't have at least 40% of the energy for your electric vehicle coming from renewables, you're actually doing more damage to the environment. Now this may sound like I'm being negative. In fact, I'm actually trying to be positive here because it's about identifying where our weak points are. And if you know where the weak points are, then we can plan for the future about how to fix these. So obviously recommendations are you got to put your processing plants closer to the point of supply if you can, or the ores. And that will do a lot of good because it's mostly in the transport. So we can reduce this 40% down to, say, 10% if we had the commitment to do so. So I guess I'll end with this last slide, some recommendations. Really, I think as we go forward, we want to make this energy transition. It's not going to happen immediately, but what's going to happen for earth scientists? Traditionally, a lot of our geologists go off to the oil industry to do exploration, hydrocarbon exploration. That sector is probably not going to grow. May not decline, but it's not going to grow. But maybe we need to focus some of our efforts into exploration. And this is where geochemistry, petrology, sedimentology, climate, everything comes into play. And it's a room for a lot of interesting research. And the other one, as I said, is the extraction efficiency. If we could make it cleaner and more efficient, we'd do much better. Bioleaching may be one of the ways to go, and that's where those of us working on biogeochemistry can play a role. And then we have to understand the environmental impacts. Those come with costs as well, not just the hydrocarbons, but also the renewables. What are those? How do we deal with them? And life cycle analysis, kind of like what we just did here. And I think earth scientists have to play a big role in this because we understand the earth system framework very well, and it's kind of behooves us to inform, say, policymakers and politicians how to move forward on this. And lastly, I would just say that it's these are some of the most interesting basic problems in the earth sciences. So even if you're not interested in applications or energy, it's just fun to think about how minerals move around the environment. Thank you.
Ladies and gentlemen, Pat Dobson.
Hi, I'm here today to give a brief talk on the opportunities and challenges associated with geothermal energy. And first, go ahead and say, what is geothermal energy? And we're really looking at mining heat from the earth. And so we're able to do that by circulating fluids through fractures and extracting those fluids to the surface. So with key requirements for a conventional hydrothermal system is to have a source of heat, to have a distributed fracture network that fluids can be circulated through, and to have fluids to be able to do that. Where do we find geothermal systems? They're typically in tectonically active areas such as subduction zones. We have arc or continental arc volcanics. We have zones of rifting in terms of mid-ocean ridges and continental rifts. We have hotspots such as Yellowstone and Hawaii. We also have areas of continental extension such as the Basin Range, where we have elevated heat flows and elevated temperature gradients. And we also have areas such as Central Australia. We have radiogenic granites overlain by thermally insulating sediments that provide elevated heat flows as well. That just means that this source of heat is shallower in the earth. We can drill to greater depths anywhere in the earth and find elevated temperatures. We just have to go deeper. So geothermal energy is available anywhere we go. So what types of geothermal opportunities do we have in store for us? Conventionally, we've been looking at high enthalpy geothermal systems for production of electricity, but we can expand our utilization of geothermal resources to a much greater extent. Part of these would be looking at sort of lower enthalpy resources for direct use for heating and cooling, for also geothermal ground source heat pumps. We can use aquifer thermal energy storage. This is used quite often in Europe, but there are more than 2,000 installations of aquifer thermal energy storage systems in the Netherlands. There's only one in the US. It's no longer active. Desalination can be powered by thermal energy. We also have mineral extraction. What Cindy was talking about was the need for lithium. If we look at the Salton Sea brines in the geothermal field in the Imperial Valley, those contain, we're currently producing brines that have lithium contents that are equivalent to 1/3 of the world's annual production of lithium. So that's an indigenous source of lithium that hasn't been utilized yet. There's a lot of research going on right now to find out commercial ways to extract that lithium from the geothermal brine. So we're really looking at an ore deposit in a fluid state. Also looking at supercritical resources. I've been work on in Iceland, the Iceland Deep Drilling Project, for looking at drilling deep to temperatures greater than 374 degrees, where we get much higher energy content, really high enthalpy fluid production. Challenges there are looking at dealing with ductile brittle transition zone. How do we encounter permeability in such a regime? And then the key objective that the DOE is working on right now is enhanced geothermal systems. Those are systems where we have hot rock, but we don't have either fluids and or permeable fractures. So we need to create a fractured network. The current installed capacity for geothermal systems that tap into conventional hydrothermal systems is approximately about 3 gigawatts. The USGS has estimated that we have approximately 500 gigawatts of resource potential in the form of enhanced geothermal systems. One way of looking at more holistically to combine all these different types of aspects has been adopted in Iceland. Michael Porter from the Harvard Business School has worked with the Icelandic geothermal community to really put together an approach where you not only generate electricity, but you look at district heating, you look at aquaculture, you look at touristic approaches such as the Blue Lagoon. So they end up with a much more vibrant geothermal industry because of that. Some of the challenges associated with geothermal systems, right now it's not very cost competitive. You see the growth of wind and solar is much greater than geothermal, and that's not because there's a lack of geothermal resources, because geothermal power is more costly right now. It's on the order of 7 to 8 cents per kilowatt hour. In the US, we're looking at solar lower than 4 cents per kilowatt hour. So there's a need for developing cheaper and less risky ways to access geothermal energy, cheaper drilling, better targeting through improved geophysical imaging of the subsurface can help lower those costs. For enhanced geothermal systems, we're looking at sort of a Goldilocks situation where we need to create enough fractures to extract fluid, but not having a short circuiting where we get one fracture that conducts the fluid between injection and production wells. So that's a current challenge that we're working on. Induced seismicity, the next speaker is going to be talking about this. In part, the slide on the image on the right is from the Pohang 2017 earthquake, which helped trigger an AGS well triggered a 5.5 magnitude earthquake. There was an earlier earthquake in Basel in Switzerland, also associated with geothermal AGS project. So being able to mitigate and manage these induced seismicity is a key concern moving forward if we're going to enhance that. And also we need to be able to balance the use of land and resources. Many geothermal resources are associated with volcanoes. We're often in national parks. So how you go about balancing is going to be a decision that society has to make. So some science and technology opportunities, improved geophysical imaging of the subsurface. There's two images. One is for electrical resistive tomography image. Another one is from micro-earthquakes from a test site underground in the subsurface of the Black Hills. Improved coupled process modeling, use of smart tracers for characterizing chemical and temperature signatures of the subsurface. We have lots of data sets. We have to be able to apply machine learning to be able to handle with these. And then most importantly, we have tech transfer we can utilize from unconventional oil and gas for improving our drilling and simulation. Thanks to the opportunity from AGU to be able to talk about this, and to Geothermal Technologies Office for providing support for our work here at Lawrence Berkeley Lab. This is an image from the Blue Lagoon. Thanks very much.
Ladies and gentlemen, Cornelius Lagenbruch.
Welcome everyone. So this talk will be about induced seismicity, and specifically I will talk about earthquakes caused by deep fluid injection in the frame of oil field operation and stimulation of deep geothermal reservoirs. So why has induced seismicity become such an interesting and fascinating research target over the past years? So induced earthquakes, they bridge the gap between very small-scale laboratory experiments and the tectonic scale. And so what is even more fascinating is that these fluid injection sites, they represent natural, unwanted large-scale earthquake laboratories. So we can study the occurrence of earthquakes under well-known and even controllable conditions. So most importantly, we know how much energy we add to the Earth's crust by injection of fluid, because we know how much fluid under which pressure we inject in a given region. And by understanding how this injection of fluid is changing underground pressure and stress, we can then actually forecast the probability of future earthquakes occurring in a given region, because it is the increase of the pressure and the change of the stresses that is unclamping pre-existing tectonically loaded faults in the crystalline basement. Thus, we have the induced earthquakes that occur. But beside all of these opportunities to study the occurrence of earthquakes, there are of course big challenges related to forecasting induced seismicity, and the biggest challenge here is the very strong time dependence of induced seismicity. So shown here, what you see is the cumulative number of earthquakes, widely felt earthquakes in the state of Oklahoma over the last 40 years. And what has been observed is that injection of fluid in the frame of oil field operation during the last 10 years has triggered seismic activity that corresponds to almost 3,000 years of tectonic activity in Oklahoma. So there is no way to forecast and analyze induced seismicity using traditional methods that assume actually long-time stationarity of seismicity rates resulting from large-scale geologic processes. So what we need to do is we need to incorporate changes of the injection rates of oil field operation to forecast how induced seismicity rates and magnitudes actually are expected to respond to it. And this is exactly what we have done back in early 2016 when the regulators in Oklahoma, they mandated a large-scale reduction of injection rates to mitigate the seismic hazard. And we actually forecasted the expected response of induced seismicity to this reduction of the injection rate. What we have done is we have calibrated the relation of past injection and seismicity rate, and then forecasted the expected response in the worst case scenario. As you can see this forecast here as the thick black line for magnitude 3 and larger earthquake and 3.5 and larger earthquake. And what you see here is that now, more than 3 years after this forecast has been made, it is actually confirmed by the observations. So the earthquake rate in Oklahoma returned to the level that has been observed between 2009 and 2013. So don't get me wrong here. So the earthquake activity is still way higher than the tectonic background, and there is still the chance that a damaging earthquake will be triggered in the future. But I think this is really a step in the right direction to mitigate the seismic hazard. Now, and if we go a step further and we develop physics-based models to understand how injection is changing pressure and stress in the underground on a very small scale, we can actually also produce maps that give us the probability of an earthquake of a given size striking in an area. And so because these maps, these hazard maps actually use injection rate as the input, we have now a tool to evaluate how future injection scenarios actually might reduce or mitigate the seismic hazard in a given region. And sometimes it's not only the high frequency of widely felt earthquakes that is problematic. Sometimes, like in the Pohang case, it's also the severity, it's the magnitude and the risk of these earthquakes. So again, here shown is the example of the magnitude 5.5 earthquake that has been triggered by deep geothermal reservoir stimulation close to the city of Pohang in South Korea in 2017. So this earthquake caused 1 fatality, 135 injuries, and $300 million in total economic impact. So in addition to understanding seismic hazard posed by induced seismicity, we also need ways to understand and forecast seismic risk. And it's very fortunate that we actually have all the tools to do this, because excellent tools have been developed to understand the risk posed by tectonic earthquakes. So what we can do already during the site selection process is we can do pre-operation loss scenario modeling using, for example, the tools like ShakeMap and Pager developed by the US Geological Survey. And if you combine this pre-operation scenario risk modeling with real-time monitoring of seismicity, we actually can compute loss exceedance probabilities in real time. Now, does it mean we can predict induced earthquakes? So the answer is a clear no, as it is also the case for tectonic earthquakes. There's no way to predict magnitude, location, and timing of individual induced earthquakes. But we have all the tools to manage induced seismic hazard and risk by quantifying magnitude and loss exceedance probabilities and accordingly adjust or terminate industrial operation. However, what is needed to do this is really a collaborative approach of industry operators, scientists, governmental authorities, and regulators. So I believe the Oklahoma case shows how this collaboration finally worked after an initial phase of denial that these earthquakes are caused by injection of fluids. In other regions, like, for example, the shale gas fields in China, the collaboration still needs to be established. Thank you.
Please. Ladies and gentlemen, William Barnhart.
I'm going to remain on the topic of induced seismicity in this talk, but I'm going to give the macro scale view as we see it from low Earth orbit. There we go. I'll venture to guess that most folks here are at least familiar with the concept of INSAR or radar remote sensing in general, mostly from examples like these. So sort of the classic examples, or hopefully future classic examples of INSAR of major earthquakes, Landers, Hector Mine, this summer's Ridgecrest earthquakes. These are just, they're observations of ground deformation induced by fault slip. And these prove to be very powerful tools in characterizing aspects of an earthquake that can be useful for understanding the hazards associated with them, such as where is the fault plane? How deep is it? Now, with recent imaging advances and more data, we can observe smaller and smaller earthquakes. So we're not just relegated to the large earthquakes. I've got two examples up here of a recent earthquake in France that was only a magnitude 4.8 circled, and an earthquake in northern Australia, magnitude 5.1 from November of this year. Sorry, those are wrong dates. The French one was on November 2019. But the key is that we can start looking at earthquakes that are at the magnitude range of classic, sort of the larger induced earthquakes in places like the mid-continental US. So what I'm going to present today is three sort of key takeaways from a statistically robust distribution of 4 whole earthquakes that have occurred in Oklahoma and Colorado over the past decade. The 2011 Trinidad earthquake in the Raton Basin of Colorado, and then a series of 3 earthquakes in Oklahoma in 2016. The magnitude 5.1 Fairview earthquake, the Pawnee earthquake, which to date is the largest known induced earthquake in the mid-continental US, and then the Cushing earthquake that occurred about 2.5 months after that. Key takeaway number 1 is these big events are basement phenomenon, using geodetic observations to map out the locations of these faults. So I'm showing 3 interferograms up here with 3 different fault models. In the bottom right, the fault models are the gray areas, the gray boxes. All of these events, through the mapping from the geodetic observations, tell us that these are events that occur within the crystalline basement, beneath the sedimentary cover that's exploited for both fluid extraction and fluid injection, and they stay within the basement. So that's important because that gives us a geologic context for where these larger events tend to happen. Piggybacking off of that, there's a hazard relationship there, which is that the depth to basement matters for the hazard in these regions. I'm showing 2 examples here, the Cushing earthquake and the Pawnee earthquake. The slip distributions again are on the left, and then the right is showing measured peak ground acceleration. Now the Pawnee earthquake was the larger of these 2 earthquakes, magnitude 5.8, compared to the Cushing earthquake, which was only a magnitude 5. But the Cushing earthquake produced substantially more damage than Pawnee, and as shown in the peak ground acceleration there, showed anomalously strong ground shaking. There's likely several reasons for this relationship, but one of the key first-order relationships is that the Cushing earthquake was simply shallower. It was closer to the Earth's surface, so it produced stronger ground shaking, which in turn led to stronger ground damage, or building damage. And because the sedimentary cover basement transition demarks that relationship between where those earthquakes are located and where they can't propagate to, at least so far as we've observed, then considering this depth to basement criteria and hazard models for the mid-continental US can provide some insights into where you might expect stronger ground shaking than in other regions. The last key takeaway comes from the Fairview earthquake, which is that the typical earthquake adjacent rules apply. So what I'm talking about here is earthquake-induced ground failure, or in the case of Fairview, liquefaction. So on the left is a larger scale interferogram of that earthquake sequence, and here there's no detectable deformation from the earthquake itself. The earthquake was too deep, it didn't produce a detectable signal. But in the river valley there, in the Cimarron River Valley, there's this really interesting signal that follows along the floodplains of the river, and that's liquefaction, or soft sediment deformation. So this is several centimeters to several tens of centimeters of co-seismic soft sediment deformation and liquefaction that occurred with this earthquake. Now, is it surprising that you have liquefaction with an induced earthquake? Absolutely not. Liquefaction is a shaking-induced phenomenon. Now, what's surprising, though, potentially here, is to the operators who installed gas wells that are shown by these black dots on the figure here, including in the region of high liquefaction, where gas wells and storage facilities move several centimeters due to this liquefaction and soft sediment deformation. And if you're building in a region where you don't expect that, you don't build to be resilient to that sort of behavior. So that's my 3 takeaways from 4 events. Thank you.
Ladies and gentlemen, to the podium, E.J. Beck.
Hi, everyone. We'll be taking a quick departure from the subsurface and focusing on the energy system. I'll be discussing transitioning to a net zero electricity system. Now, in 2018, IPCC published a special report that indicated keeping global average temperature increase to 1.5 degrees C would require global greenhouse gas emissions to reach net zero by 2050. Now, the electricity sector is critical in meeting this goal. And that's because electricity, as of today, currently comprises of 30% of global greenhouse gas emissions. And decarbonizing other sectors of the economy, such as transportation or heating, may also depend on decarbonizing the grid. So there's no better place that exemplifies this effort of decarbonizing the grid and electrifying other parts of the economy than in California, where we are today. California has a goal to reach a net zero carbon grid by 2045 using 100% clean energy sources. It also has an executive order in place to reach 5 million zero-emission vehicles by 2030, and California agencies are actively looking at electrifying buildings as a decarbonization strategy. As the 5th largest economy in the world, and with many climate policies in place, I believe California is the optimal place to understand pathways to achieving a net zero emissions grid. And that's exactly what we've done. We used a detailed capacity expansion and dispatch model to understand and assess the cost-effective pathways to achieving a net zero carbon grid in California. And the bottom line is, we need clean, dispatchable resources. Now, we'll come back to this, but first, let's look at renewable resources. Solar, wind, and lithium-ion battery resources have seen cost decline by 40 to 90% in the past decade, which is remarkable. And it's really opened up the possibility for these resources to contribute significantly in decarbonizing the grid. However, solar and wind resources are still highly intermittent and variable. And while lithium-ion battery sources can help short-term intermittencies, they're still insufficient to help solve long-term seasonal differences in generation patterns. And so what we found was that increasing the share of renewable resources in the grid and only decarbonizing the grid using renewable resources drastically increased the cost of the system. And that's because we had to overbuild the system to ensure reliability for the entire year, on the order of 3 to 4 times in capacity than the peak demand. Now, this has significant land implications for California as well, but fundamentally, it's a lot more expensive than the system that we have today. Now, alternatively, if we add a clean dispatchable resource, and in this case, I'll be focusing on gas power plants with carbon capture and storage, and dispatchable resources assuming it can generate electricity when it's called upon, then we find that the cost of decarbonizing the grid decreases drastically. And when I say drastically, I mean it's half of the cost of a renewables-only system in meeting a net zero carbon grid. Now let's think about why that might be the case. In the scenario with the dispatchable resources, we still see that solar, wind, and battery resources play a significant and very important role in decarbonizing. But what that dispatchable resource does is generate electricity during hours when the solar or wind is not available. Now, in California, we have a lot of sun. So this means that the dispatchable resource generates electricity during the nighttime when the sun is not shining, and during the winter months when the sun is not as strong as in the summer. And so this dispatchable resource greatly prevents the overbuilding of solar and lithium ion battery capacity and reduces the cost. Now, when I say dispatchable resource, it doesn't have to be only gas with carbon capture and storage. It could also include enhanced geothermal or geothermal resources, nuclear power, or any other zero carbon low liquid fuels as well. Now, as I mentioned before, we really need to decarbonize the electricity system. And it's important that we do it cost effectively because it really directly impacts our lives. And there are many moving pieces to meeting this goal. And what we found is that one of the most important puzzle pieces to ensure a cost-effective transition is a dispatchable resource. Thank you for your time.
Well, that was a great set of thought-provoking discussions here, or presentations, and so we'd like to have some discussion following this. Any questions from the audience? I see one over here. Where's my microphone? I can yell. Wait, she's coming.
EJ, when moving to a carbon-free grid, you looked at supply side, but did you consider demand side reduction or modification at all so that you're offsetting that big bell curve?
Yes, definitely we have. And demand is definitely a big driver of overall costs, but we do find that that trend persists regardless of the demand shape or to overall load as well.
So the last speaker talked about reducing the carbon footprint, but zero emissions, California, et cetera, like vehicles. But the first speaker, I think, talked about how those batteries, for example, for Tesla, there's a lot of, I mean, it's not clean really when you add everything up. So I'm wondering if California is looking into that as well, because if you just only look at one end and not the other end, then it's not really a clear picture.
Yeah, no, thank you for the question. I think that's definitely a great point. I think they have been looking at supply side emissions as well. To what degree that's reflected in the policy, I'm not sure yet. I think of California kind of pushing all fronts on a lot of its different policy measures. So I'm sure it's also doing some work to understand, but I'm not really quite sure exactly what right now.
So I'd like for EJ maybe also, sorry.
Okay, we'll come back.
It's right here. In terms of the storage, I don't think we have to, particularly as geoscience, to just think about battery, right? I mean, we could also think about, Pat alluded to it a little bit, subsurface energy storage via thermal, via compressed air, via hydrogen, things like that. I think, is that included in your study too as a potential pathway rather than the dispatchable renewable?
Yeah.
Not dispatchable clean.
Yes. So a couple of the ones you've mentioned we've included. We've included long-term duration storage, but that's still kind of order on the couple of hours. We've also tried modeling hydrogen and ensuring that the hydrogen comes from electrolysis and renewable resources. And at least in the scope of an electricity grid model, hydrogen itself doesn't do as much because it's still very expensive. And so when incorporating the costs of these technologies, it still comes out that dispatchable resources are the cheaper option. But definitely a lot more work can be done, I think, in modeling a lot of different other technologies out there.
Yeah, the question about lithium. So I guess if you put your refinement closer to the source, you can reduce all these carbon footprints. And I guess Elon Musk must be thinking just that by putting the factories near some of these potential resources or reserves in Nevada. The only problem with Nevada, there is lithium, but you need water to extract that lithium. And so there's a number of companies that have gone in to buy all the different rights, and only one company is smart enough to buy also the water rights. So there's also going to be issues of competition for water that's used for other needs. And then for energy storage, if we can get off of lithium cobalt batteries, and there are people trying to find new technologies that you don't need cobalt. Cobalt is actually really the limiting agent here, and using sulfur instead, and there's plenty of sulfur. Then we're really, that would be a revolution and a game changer.
I've got a question for the, I guess it kind of goes with the last three speakers. Carbon capture and storage, if I understand what you mean by that, involves pumping a lot of CO2 underground. And there's lots of data that shows that the number of, the biggest size of an earthquake correlates with a magnitude, with the volume of fluids that's pumped underground. So if we end up pumping the amount of carbon underground that we would have to do in order to make any difference, it seems to me like the induced earthquake problem is just going to get a heck of a lot worse. There's always also the question of whether or not the carbon is going to stay down there for a period of time that's of any use to us. But
okay, so maybe I can give an answer about the US. I can answer about the earthquake hazard. So, I mean, right now, carbon capture and storage is in a testing phase, just very local scale injection, and the volumes are just orders of magnitude lower than the volumes we need actually to do something about climate change. So, if CO2 would be injected on a very large scale, so it might be possible that we will have a scenario like in Oklahoma, where not CO2 but water is injected over a very large scale over the complete state. And yeah, it might be a problem if these volumes of injected CO2 increase orders of magnitude like it is right now predicted. So these are the volumes we need actually to reduce the CO2 concentration in the atmosphere.
This question is to Dr. Lee. Can I ask one here? Hello? So your conclusion was we did not have enough solar or wind to give us all the energy we need. So we need coal, oil, and gas. Is it possible to go from coal to natural gas? We can get a lot of that from unconventional sources. That would give you half of the CO2 that you can get from coal. This could be a transition period from, for a while until we develop some other methods.
Yeah, I think these unconventionals, no one ever would have predicted that the U.S. would be producing so much hydrocarbons. But really, they're just a transition. Ultimately, we want to go towards a fossil fuel-free state, and there are these challenges that we have to meet. It's possible, but we have to tackle them. But in the meantime, it can't happen overnight, and so you're going to have to still burn some fossil fuels. But getting off of coal is one of the first steps in going into these unconventionals. It's cleaner. It comes with its own problems with fracking and induced seismicity, of course. Nothing's perfect.
I have a quick question about using existing infrastructure. So in the North Sea, in Europe, there's quite a lot of CCS-type operations going on, as well as the UK Geoenergies project, where basically either dried oil fields or old mine works were used to sequester carbon and store energy. Some of these are still in testing phases. I was just wondering, for the calculations for economic benefits, is that something that either of you guys are considering for future, for California plannings, for example?
You mean business opportunities for CCS? Is that kind of...
No, I just meant in terms of cost-benefit analysis, how you can use existing infrastructures to save money.
Well, the thing about, at least in California, CO2 pipelines, we don't have any, and that would require building new ones, so that's incorporated into the model. At least looking at the electricity sector, it does take into the cost of existing infrastructure, because we're assuming retrofitting existing gas power plants with carbon capture and storage. And so that's part of probably where the cost, a little bit of the cost reduction comes from. Although we have also run cases in which we've assumed that we have to build new CCS power plants, and in those cases it's still a lot cheaper. So we've kind of done it in that analysis in the scope of the electricity system model of how we can best incorporate the costs, but that's actually something that I'm looking into the future as well.
Okay, go ahead. Julie, we have time for one last question, please.
I'm always wondering what happened to the lithium battery, the first generation of Tesla. What happened to their batteries? And my understanding is that you're not using the lithium. What's the state of our art or technology to recycle them?
Unfortunately, I don't know what the state is in terms of recycling, so I can't really answer that. But my sense is we're not doing a good job of recycling them. But we're going to have to recycle all of these. It's a global recycling, and doing it all in the U.S. For our own purposes. Yeah.
Thank you for that good discussion, and let's thank our speakers again. And I do believe that these talks are being recorded, so if you missed some of the morning talks, you'll also have the opportunity to revisit some of them later. So thanks to everybody.
Our thanks to our panel. Their conversation will continue in the networking area on the other side of the wall to your left. By the way, at 6:15 this evening, AGU will present a world premiere of a film by Kendall Moore right here in the Inspire Theater. Please join us then. Thank you.